Swayam Prabha. Digital India. Educated India.
We will start today by talking about some similarities we have between the three transport processes, okay, and then we will look at this. So, we have the conservation of momentum, and this is basically your Navier-Stokes equation, where you write du by dt plus u dot gradient of u equals plus mu del square u, okay, plus rho g. So, this is the momentum balance which we have used so far. In fact, we derived this momentum balance in the class, okay, from starting from Reynolds transport theorem. What we want to do is, I want to just write down the analogous equations for energy and for mass or species. So, conservation of energy will be equals k del square T, okay. And if you look at a species balance, you will write dC by dt plus u dot gradient of C equals d del squared C, okay. So, this is typically what we write, and what this is doing is, this basically the way you normally are used to thinking about this is, the time derivative term takes into account the accumulation of either species or energy or momentum, okay. This is the accumulation term. In a control volume. What does u dot del C represent? It represents the flow, because the change, the flux across the control surface through convection, okay. This is convective flux, and this is your diffusive flux. So, I have just, so if you wanted to, if you know your Navier-Stokes equation, you can just write the energy by representing this u with T and this u with C for the species balance, okay. And of course, this is your diffusive flux. Now, let us look at, if I want to divide this equation by rho throughout, the del square u will be multiplied by kinematic viscosity, which has units of meters per second. If I divide this by rho Cp, I get k by rho Cp, which is alpha, the thermal diffusivity, okay, which has units of meters squared per second, and this of course does not have anything, this also has units of meters squared per second, okay. So, basically all these are called diffusivity, okay. So, mu by rho is nu, k by rho Cp is alpha, and d have units of meter squared per second. Okay. Now, in this particular problem, okay, we have this, so you might see this equation with some extra terms sometimes, okay, and for example, this is the pressure gradient, the pressure difference which drives the flow. If there is no pressure gradient, the flow is not going to take place. So, this is the like a source term, okay, this is a pressure gradient, okay. So, here normally we are used to this pressure gradient delta P is the source term to drive the flow. There may be problems where there is no pressure gradient, but still you have flow. For example, the Couette flow problem where you have one of the walls moving, okay. So, you can possibly have a flow situation even without a delta P, but something has to generate. It could be the Couette flow. Now, another situation where you can have flow is because of the body force, okay. So, okay, if delta P is 0, we can still have a flow like in the Couette flow, okay, or rho g, the body force can give flow. We saw that problem where we had that vertical wall in which the gravity was dragging the fluid down, okay. If you remember long time back we spoke about that problem. Now, in addition to these forces, these body forces, there could be other forces also depending upon the nature of the fluid. For example, if your liquid contains ions or contains a ferrofluid contains magnetic nanoparticles, okay, then if you were to apply an electric field or if you were to apply a magnetic field, that will also induce forces, okay, and that can give rise to fluid flow. So, basically what I am saying is you might see papers or articles where some extra terms may come in depending upon the particular situation. You might get in the presence, so there is a field called electrohydrodynamics, there is a field called magnetohydrodynamics where people put a magnetic field, put an electric field, you will get extra forces here, okay, and you have to go back and go back to whatever you learned in your physics, your different laws for how Lorentz force, how do you calculate the forces, and then you have to include it here, okay. So, basically we can have other forces like electric field and magnetic field to generate flow. So, and depending upon the particular situation you have to include the physics. Now, similarly when it comes to here the energy balance, you can have a source for heat, okay. For example, if there is a chemical reaction which is exothermic or endothermic, if it is exothermic there is a source for heat, it will liberate energy, okay. So, that is something which you have to add. Right now this is without any source term. So, in the energy balance we will have a heat source. So, could be exothermic reaction. So, if you have an exothermic reaction, you have to write that term as the heat of reaction delta H multiplied by the rate of reaction, Arrhenius kinetics, Okay, that could be one way by which heat is generated. Another way which is commonly another thing which is frequently encountered is when you have viscous dissipation. So, viscosity, remember, is something like friction, it prevents movement, right. So, you have friction when two layers are moving side by side, heat is generated. So, similarly in a fluid flow, because of viscosity you can have heat generation. Okay. So, this is usually added here. So, heat viscous dissipation what is this? Heat generated by viscous effects. So, if you have a fluid flow in a pipe, you will have viscous effects, and if the fluid is sufficiently viscous, okay, you will have heat generation added. Like for example, you have Joule heating. Joule heating, what is happening? Because when you have electrons going through a conductor, heat is being generated. That is because of friction, the electron is moving and there is some resistance to it. Okay. So, similarly an equivalent of that is viscous dissipation. So, viscous dissipation is something, and that will always be positive. Okay. So, in fact, if I feel I might derive it. So, you can have those will get added here. Okay. So, you can have source terms, these are the two source terms which are written here, reaction and viscous dissipation. Similarly, for species balance, when you consider again a chemical reaction, depending on whether it is a reactant or a product, it is going to be a source term or a sink term. Okay. So, in species balance, okay, we will have the same thing. I do not think I need this. In the species balance, we have a source or sink due to chemical reaction. Okay. So, again you have a source term. So, my point is the time derivative terms on the left, they are kind of standard, you can neglect them under some cases, steady state, stuff like that. Then you have the convective flux, you have the diffusive flux. In addition to that, you might get some extra terms depending upon the physical problem. Okay. And when you see equations, you have to try to figure out what is the physical meaning for these terms. Okay. So, now that is the general thing we have. I thought what I will do is, rather than talk about deriving all these equations, solve one or two problems. Okay. Then maybe we will come back and derive the equations. The problem we are talking about is a one dimensional flow in a pipe where the there is a constant flux of heat. Okay. So, we have a pipe here, this is the z direction, this is z equal to 0, this is z is negative, and this is z greater than 0. Okay. I have a liquid which is flowing in this pipe, and let us say that the Reynolds number is sufficiently low, okay, so that the flow is laminar. Okay. And a circular pipe. okay. And the radius of the pipe equals A. And laminar flow. So, when I say laminar flow, what do I mean? I have a parabolic velocity profile. Okay. So, my pipe starts from z equal to more than 0, that is the area of interest. To the left of z equal to 0, for z negative, I am saying my pipe is insulated. But, so this portion is insulated, okay, and in this portion there is constant heat flux. So, heat is being supplied. So, I am supplying heat to this pipe, and let us say one way to supply heat is to put some tape around it, pass electricity current, okay. Like I said earlier, you have joule heating, heat is going to be released and that heat is going to go into the fluid, okay. So, the problem is liquid is flowing, it is entering at a particular temperature, let us say T naught, okay, and I have a velocity profile which is established here. Here there is not no heating going on, everywhere here temperature is constant T naught, okay. Here temperature is T naught because it is insulated, no heating. But once it enters this portion, it is going to be subject to this heat flux and temperature has to increase, okay. So, what we are interested in is trying to find out how does the temperature change along the pipe, okay, and temperature is going to change both radially as well as axially, that is the question, that is the object of interest. So, question is how does T change with R and Z. And to keep life simple, I am assuming that things are axisymmetric. So, there is no theta dependency, that is the reason I am not putting theta, otherwise in the cylindrical coordinates you will have all the 3 variables r, theta and z. So, I am just forgetting about theta for now, okay. So, basically we are saying theta symmetry. So, the first thing you have to understand is that when the temperature is increasing, okay, the physical properties of the fluid like viscosity are going to change, okay. And for example, viscosity is a function of temperature, more the temperature the less is going to be the viscosity. And when we derived this laminar flow velocity profile, we had assumed viscosity was constant, okay, and then we did the calculation, got the profile. So, clearly the first question is, can I even use the laminar flow velocity profile, because I have to go back and re-derive my velocity profile by including viscosity as a function of temperature, okay, because viscosity will change. So, this whole concept of fully developed flow is not even valid. So, the point I am trying to going to make now is, there are 2 ways to solve the problem. You have to be very clear about what exactly is of interest to you, what is your focus, okay, what is it that you really want to find out. So, one way is to include all the effects, put viscosity as a function of temperature, put specific heat as a function of temperature, put density as a function of temperature, and because all of these properties are going to change. Or when it comes to modeling, the basic funda is that you need to keep the model as simple as possible, but not too simple that you get a trivial solution. Keep it as simple as possible, but retain all the important effects, okay. So, I want you to understand that there are certain assumptions which are being made in what we are going to be doing today, Okay, it is not that. So, the assumptions are, I am assuming properties are independent of temperature, for example. So, as long as the properties are independent of temperature or they are weak functions of temperature, whatever I am going to do is fine. But if the properties are going to change significantly with temperature, then whatever I am going to do may not be valid. Okay, so keep that in mind. So then, so the whole art, so whatever we are doing, writing down these model equations on the basis of certain assumptions is basically what is called modeling. Okay, and in modeling you want to keep the important physics and try to solve the problem, try to predict the solutions, try to analyze the problem. You get some results, you get some interpretation, and then you see if it makes sense. If you made too simple, then you may get you may not get any insight. You make it too complicated, then you won't get any insight because there are too many things changing. You do not know what is the exact thing which is causing, what is the most important thing which is causing your behavior. Okay. So, in modeling, the one thing which we want to do is understand what is happening in the problem and retain what is the important physics. So, that is the whole point here. Okay. So, viscosity is a function of temperature. So, can we use the laminar flow profile? Ideally, answer is no. Okay, because the laminar flow, because the parabolic profile assumed viscosity equals constant. Okay. But supposing viscosity is a weak function of temperature and all other properties are also weak functions of temperature, then I can possibly treat these properties for all practical purposes as constant. Okay. So, if viscosity, density, specific heat are weak functions of temperature, we can treat this as a constant. And so, this is the whole idea of modeling. Okay. So, in modeling we make assumptions simplifications to get some physical insights. Okay. So, we need to focus on the important physics. Your model has to capture the important physics. Okay. So, for the purposes of so if density as a function of temperature is important, then you need to include that. For example, if you are talking about a problem where natural convection is important, okay, natural convection is going to occur because of density gradients, right. You have a hot liquid at the bottom, cold liquid at the top, and because the hot liquid has a tendency to rise, it will come up and then you see convection. Now, therefore, in that problem you have to consider density as a function of temperature. You cannot say I am going to assume density as constant, I mean, you can say density is constant, but then there won't be any natural convection. So, keep that in mind. So, depending upon the particular problem that you are actually solving, you want to include the physics. So, in natural convection, I will have to include density as a function of temperature. If I assume density is constant, no natural convection is going to occur. So, I am basically defeating the purpose. So, you can't make arbitrary assumptions. So, everything that you do has to be done with sufficient thought, okay, and only then you can possibly proceed towards a meaningful solution. That is the point I am trying to make, okay. So, in natural convection, rho as a function of temperature must be included, okay. We cannot treat rho as a constant. So, depending upon the particular problem you solve, you proceed making assumptions. So, now we come back to our problem. So, to cut a long story short, we are not going to worry about the fact that the viscosity is going to be changing with temperature. We are going to assume the laminar profile is valid for our problem, okay. So, then you have this great fluid where viscosity does not depend upon temperature, okay. So, then the laminar flow velocity profile is valid, and we are going to use that and proceed with the solution. So, keep that in mind, some assumption is here, okay. So, now I come back to the problem here. I am interested in the temperature profile. I am telling you it is a one dimensional flow because it is laminar, okay, and I want to find out how does the temperature change with R and Z, and let us say keep life simple, stay steady state, okay. So, how do I go about doing this? I need to write my energy balance equation. So, energy balance equation tells me rho Cp times dt by dt plus u dot gradient of T equals K del square T. So, there is no chemical reaction or anything occurring in the liquid. If there is a chemical reaction occurring in the liquid, then I have to add a source term, okay. Now, the only way the heat is coming is through the boundary. So, it is going to be reflected in the boundary condition, okay. I am assuming the flux of heat is constant along the pipe, okay. So, where is my generation of heat is coming through the boundary condition, okay. So, there is no source of heat in the domain, and heat enters through the boundary condition, okay. Earlier I spoke that there may be some reaction, then some source term has to come in. So, now let me get rid of this steady state. So, this goes off because of steady state. At steady state, I have rho Cp, and there is only one velocity component, which is the axial velocity component uz, okay. There is uz dt by dz. This is the only term which is going to contribute here, okay. This is u dotted with gradient of T, only component is uz, other velocity components are 0, okay, because we are assuming fully developed flow. So, that is the advantage of that assumption we made, viscosity is constant. And here I have K times Laplacian is 1 by R d by dr of R dt by dr plus 1 by R square d square T by d theta square, oh yeah, plus d square t by dz square. Yeah. Again, because of theta symmetry, this is 0 because of theta symmetry. So, basically what we are trying to tell you is we have convective flow flux of energy and we have diffusive flux in the r direction and the z direction. Okay. This is the energy balance. So, if you look at a shell, I have flow which is bringing in heat. So, if I take a small shell here of thickness dz, this is telling me what is energy coming in, what is energy going out. Okay. And this talks about the diffusion. This is because of convection, and this talks about diffusion in the radial direction and diffusion in the axial direction. So, everything is going to getting balanced at the steady state. You will have steady state only when all these fluxes are balanced. If there is an imbalance, then there will be accumulation and you will have the time derivative term. Okay. So, that is what it is. And what is uz? It is 2 times u average times 1 minus r squared by a squared. This is my parabolic velocity profile. You are used to writing it in terms of u max. Okay. But in cylindrical coordinates, u max is 2 times the u average and capital U is my u average. Okay, this is my velocity profile. This is coming from my laminar flow by solving the Navier-Stokes. So, basically what I have done, if you look at it mathematically, by making this assumption of viscosity is independent of temperature, I have decoupled the momentum equation from the energy equation. If viscosity is a function of temperature, I have to solve the momentum equation, the Navier-Stokes equation and the energy equation simultaneously, because now viscosity will have temperature, energy equation tells me temperature. So, both of them are coupled. So, by assuming viscosity is independent of temperature, I solve Navier-Stokes, get velocity profile, substitute it in the energy equation. Okay. That is the mathematical thing that we have done. So, this is my this thing. So, what I want to do is I want to substitute this velocity field here and I will divide by rho Cp and call this thermal diffusivity alpha. Okay. So, I am going to write 2 times u times 1 minus r squared by a squared dt by dz equals alpha times by r. This is what I wanted to mention. Okay. This alpha is K divided by rho Cp or thermal diffusivity. Now, what I want to also mention is this Laplacian, the way I have written it is for a scalar, because I am talking about temperature, and although this is a cylindrical coordinate system. Okay. Remember when we were talking about Laplacian earlier in Navier-Stokes equations, we got some extra terms. Okay. But here there the Laplacian was operating on a vector. So, that when you were operating on a vector, you had to worry about the change of the unit vector with theta and all that. But here temperature, concentration, they are all scalars. Okay. So, there is no question of unit vector, and when you are differentiating with theta, there will be something else coming up. So, that is the reason this Laplacian is going to be of this form. So, I mean I just wanted to point out that to you, that this is what we mean by Laplacian, and spherical coordinates, remember we said you will get e squared, e power 4 instead of del power 4. Okay. So, all this is connected. So, keep in mind, if you are operating on a scalar, this is Laplacian. If you are operating on a vector, you may get a different this thing depending on the coordinate system. Anyway, so that is just to, I am just trying to put all the pieces together so that you are hopefully your improvement clarity improves. Okay. So, now before I proceed, I want to specify the boundary conditions. Temperature at z equal to 0 is T naught. Okay. And because it is second order in z, I must say dt by dz tends to 0 as t tends as z tends to infinity, something like that, okay. And you will see that this boundary condition is something which we are not going to worry about. So, I am not spending too much time trying to explain this, okay. And at r equal to 0, temperature is bounded, and at r equals a, r equal to 0 is the center of the pipe, r equal to a is the circumference. I have constant heat flux, okay, and I am talking about a situation where I am heating the liquid. So, I have Q, my heat flux, okay, it is coming into the liquid. So, the flux is in the negative r direction, must be equal to K times dt by dr. So, that basically yeah, that is your boundary condition. This is the one which is generating the heat for me to have the liquid get heated up. So, I want to, so I mean you could actually solve this problem, okay, because you have the initial conditions, the boundary conditions, you can write the numerical code, you can possibly solve it, okay. Now, but I want to see whether I can make some simplifications, okay, and that is the whole point of what I am trying to do, because this is a kind of, this simplification is normally made in most problems where you have both convection and diffusion. So, this problem we have both convection and diffusion, okay. So, although this problem is got both the terms, this problem is a linear problem. Why? Because all the terms are occurring to the power 1, because this velocity is known. The other complication is that this is got variable coefficients. If it is a plug flow, if it is uniform velocity field, then this will be a constant, u average multiplied by that, okay. So, this is a function of r here, and this is the stuff which is here. Now, since I am interested in seeing some simplifications which I can make, what you want to do is you want to make equations dimensionless, to look at scales, to see if I can neglect some effects, if I can neglect some effect, so that I can simplify things, okay. So, let us make this equation dimensionless. So, limiting cases means very fast convection, very slow convection, that kind of a stuff, very fast diffusion, okay. So, then I may be able to simplify things and I may be able to get better insights. That is what I mean by limiting cases. So, now clearly the characteristic length r star, the dimensionless length is going to be defined as r by a, because in the radial direction I have the length, diameter of the pipe, the radius of the pipe as my characteristic length scale. Now, I mean if I have a very long pipe, I really do not have a characteristic direction in the z direction, but since I do not have anything, I am going to just take the same scale for z as well, okay. So, z star equals z divided by a. So, I am choosing the same length scale for both r and z, yeah. Then what is remaining is only my temperature has to be made dimensionless, two independent variables r z and one dependent variable temperature. So, theta is my dimensionless temperature, which I am going to write as T minus T naught divided by temperature is, if I make this dimensionless, I will get A and K at the bottom. So, I will get d theta, yeah. So, temperature I am going to define as T minus T naught times Q A divided by k. So I am talking about so if I use this as my temperature scale, what will be my boundary condition? I am saying, so if this is the boundary condition, then this is a dimensionless scale at z equal to 0, T was T naught. This implies theta equals 0. Okay. My fluid was coming in at a temperature T naught, but now I am talking about making theta defined this way. So if T is T naught, theta must be 0. That is my inlet condition at z equal to 0. What about the boundary condition? Of course, if T is bounded at r equal to 0, T is bounded, so theta is also bounded. Bounded means finite, it is not becoming infinity. Okay. And at r equals a, or r star equals 1, r equals a corresponds to r star equal to 1, I have q equals T dt by dr, right, d theta by dr star. Wait a minute, q is k dt dr, k times dt is qa by k d theta, again a here dr star. Okay. So what you get is k cancels with this k, q cancels with the q, a cancels, and you get d theta by dr star equals to 1. What I have done is I have just converted all the boundary conditions and the differential equation to theta. Okay. Now I have not done the differential equation yet, I have just converted the boundary conditions. So this becomes now, so the boundary condition at r star equal to 1. So basically at r star equal to 1, I am saying I have d theta by dr star equals 1. That is my dimensionless boundary condition. I will make the boundary conditions dimensionless, I will make my differential equation dimensionless. Okay. So now I am going to do this, this is just r star squared, r by a is r star, and dt by dz, I am going to write this in terms of d theta by dz star, and when I make z star dimensionless I get a, and when I make t dimensionless I will get qa by k. When I am t minus t naught, the derivative of t naught is 0 because t naught is a constant. Okay. So this is qa by k. So qa by k comes from converting t to theta. Okay. So you can just think of differentiating this whole thing. T naught is a constant, does not contribute. Again here I have alpha times, you can do this, okay, a squared, because there are two, basically the second derivative, so each will contribute a factor of a, and I am using the same scale for both a and z. I will get an a square out, I get 1 by r star d by dr star times r star d theta by dr star plus d square theta by dz star squared, and since I have converted t to theta, I will again get a qa by k. Okay. And it is not t, it is derivative of t. So this t naught does not contribute. So when I differentiate this on both sides, I will get a qa by k here. So there is a qa by k. So now this qa by k cancels off, and I have 2 times u, there is one a here, there is an a squared here. I am going to bring the a squared alpha to the left hand side. So, 2a by alpha okay, that cancels with that. So this here is a dimensionless group. This is units of meters per second multiplied by meter squared per second. This is also meters squared per second. So this is called Peclet number. So you can think of Peclet number as the ratio of two things. One is the convective transport, because u is velocity, it talks about convective transport. Alpha is got k by rho Cp, it has thermal diffusivity. Okay. So basically it talks about conductive transport. So Peclet number basically is a measure of how important is convective transport over conductive transport. Okay. So to rate of so far I can actually solve this equation. So I can write this as 2 times Peclet number, this thing. I have not made any simplifications or assumptions. Okay. So the whole purpose was, I mean, when you make it dimensionless, if you want to, you can solve with all the terms, whichever is important. But you may want to see in a certain problem, maybe certain effects are not important. So you want to make simplifications. For example, if Peclet number is very large, if Peclet number is very much less than 1, very small, what does this mean? U is small, u is low. Okay. That means flow is very small, the convective transport is very small, slow, conductive transport is high. So I can neglect the left hand side. So here we can put LHS to 0 and we end up solving 1 by r star squared. I will just write this del star squared theta. Del star means all the directions r and z are in terms of r star and z star. Okay. So that is my equation, this is my conductive equation. Okay. So that means in this particular problem it is only conduction which is important. So this is the case when the Peclet number is very, very low, when the convection, the fluid velocity is very small. Only transport that is going to take place is because of conduction. Okay. The del square T term. So there is conductive transport in the radial direction, there is conductive transport in the z direction. Now I will just do one more thing and we will stop. If Peclet number is very much larger than 1, what do I get? So I would divide this entire equation by Peclet number. Okay. You divide this entire equation by Peclet number is very large. So and if you have done the scaling properly, all these are going to be of order 1 and so the right hand side will now be set to 0. Okay. We divide equation by Peclet number and what do you get? 2 times 1 minus r star squared d theta by dz star is approximately 0. We are assuming that all of these are going to be of order 1, so that is not going to go up to infinity. I am dividing by Peclet number which is large, so that becomes 0. So this means the temperature is not changing in the z direction. So in this limit, I have a problem in the sense this implies theta is 0 in the pipe, okay, and there is an inconsistency here because I am supplying heat and there is no change in the temperature. One way to argue is the liquid is flowing so fast that it is not spending enough time to absorb the heat. But I mean, you are looking at a case where it is flowing fast, but it is also absorbing heat. So you want to find the temperature, it is not flowing at an infinite flow rate, it is flowing at a large flow rate. So there will be some amount of temperature increase in the pipe. So what this basically tells me is that this particular scaling that we spoke about earlier, choosing the same length scales in the R and Z direction, okay, is the problem. So we possibly have to go back and look at the scaling to overcome this. So you understand what the problem is. When the liquid is flowing, when Peclet number is high, I am saying there is no temperature increase, d theta by dz is 0, but I am supplying heat. So something has to happen, the temperature has to increase, okay. And the way you resolve this problem is by doing a rescaling, defining the length scales in the R and Z direction in different ways, okay. So that is what we are going to see tomorrow.